my slides into the chat so folks can follow along if they would rather do it themselves rather than wait for me to turn the pages. Hi, I'm Donald. I work out of the San Francisco area. So it's 7 in the morning for me, unfortunately, but I'm happy to be here. Basically, I put together a talk to discuss the differences between Go and Java, just as a using Java as a reference point, since it's a relatively popular high-performance programming language. One of these days, I may also do a similar talk for Node.js. Let me go ahead and start presenting my slides.
Just one question: do you prefer to get questions straight away or at the end? It's always we ask.
If there's any confusion, ask questions straight away. But if you have questions about anything that you want me to go into more detail, I'd rather you hold them to the end.
Okay, thank you. Go ahead.
All right. So one of the first places that there's a noticeable difference between Go and Java, of course, is the standard library. Here are some of the things that Go has as an advantage over Java. The Go standard library has built-in support for HTTPS servers and clients, with both support for both HTTP2 and TLS 1.3, which are the latest versions of each and are significantly different from the previous versions of those protocols. I believe Java has finally added a decent HTTP client out of the standard library, but to my knowledge, there still isn't a built-in HTTP server. Another nice thing that Go has that Java does not is HTML templates. In particular, HTML templates that do context-sensitive auto-escaping. That way, you have a guarantee that you aren't accidentally introducing security problems like content-site script, cross-site scripting attacks and content injection and things like that. One nice thing that Go has is it has a built-in standard library JSON encoder and decoder that can do structured types. In Java, you usually end up using either Jackson or JSON, both of which are monsters to use. Go also has a very basic support for XML encoding of structured types. It's not the sort of thing that you would use to deserialize arbitrary XML, but if you want to create an XML format for some existing structured types that you have, the Go XML encoder is pretty useful. Go has support for modern cryptography primitives, and the Go standard library is a lot easier to use than OpenSSL, and also a lot easier to use than the equivalent cryptography standards in the Java standard library. And then Go also has robust support for low-level Unix operations, path stuff like stat change on change mod, which Java added relatively recently, but people still aren't using Java NIO files paths very much. And Go also supports subprocesses in a much more robust way than Java does. You can actually do things that you would do in the subprocess module of Python, for instance. And Go supports signal handlers, which Java does not. Go also has built-in equivalents to array list and hash map. So you don't have to go hunting around in the standard library for those. They're just available without any imports. On the other hand, Java does actually have some advantages itself. The Java collections library in Java util is a lot more complete than anything offered by the Go standard library. The Java standard library has lots of support for generic types, but Go didn't get generic types until Go 1.18 was released earlier this year. Java supports a nice inline syntax for lambdas. Go supports anonymous functions, but it doesn't actually have a lambda syntax. So using function callbacks can be pretty obnoxious in Go. Java supports anonymous classes that implement a named interface. For Go, if you want to implement any methods on a type, you have to actually give it a name, and that name has to be declared at the top level of your current package. And Java supports custom iterable types. In Go, only built-in types can actually iterate. You can build your own iterator, but you won't have the nice 4-item in range syntax that Go provides. Object-oriented programming is extremely different from Go to Java, or vice versa. In particular, Go's philosophy is interfaces, not inheritance. So Go interfaces describe a collection of methods that a type has to implement. Go types do not need to declare which interfaces they implement. It's automatically determined based on the methods that you've implemented. When you try to use a value as a specific interface, Go will check at compile time that the interface is implemented by the values type. And then it will automatically synthesize whatever internal bridging stuff it needs to make sure that that type can be used as that interface anywhere else in the program without, in technical terms, it's synthesizing a vtable for all the methods that are available through the interface. Versus Java, a huge difference is that Go does not have inheritance. Go does have something called anonymous struct embedding, which is not quite the same thing, but it can be used to graft default method implementations onto a type. So you can declare an anonymous struct that implements some methods, and then you can declare some additional types that embed that anonymous struct, and they will get those method implementations for free. But those default methods don't actually work like an abstract base class because they can't actually call your methods on your type. They can only refer to the fields within the anonymous struct and to the methods already defined on the anonymous struct. So here is a worked example of a type that implements an interface and that has an abstract base class. We have 2 methods called sum and product, and the sum and product are computed over 2 integers. For the sake of the example, we concretely implement the sum method in the abstract base class, but we leave the product method undefined for implementations to override. And then in the derived class, we actually implement product. And then this is what it looks like when you actually use that code. You construct it using the public constructor, which I actually omitted from this example. Oh, actually, I'm using Lombok. And then you can call the sum and product methods on that type. Here is something relatively similar in Go. We're declaring an interface of sum and product that each return an int. We're declaring an anonymous struct called abstract foo that we're using as if it were an abstract base class. And we implement sum on the fields in abstract foo. And then in the derived type, we actually embed a copy of the abstract foo type into our type. So then when we implement the product method, we can refer to the fields inside the abstract foo as if they were our own fields. And likewise, any methods that were implemented by the abstract type also become our methods. And at the very bottom, I have an example of syntax that's very commonly used as a compile time type assertion, which is a way of asking the compiler to confirm that the derived type can actually be used as the interface, that it implements all of the methods. That can also be useful as like a executable way of telling people reading the source code that you're intentionally implementing a given interface. And here is an example of actually using that type in practice. As you can see, the fact that abstract foo is embedded does not, even though it's anonymous, it doesn't mean that that it's transparent. You actually have to construct the inner struct and then give it as an argument when constructing the outer derived type. So it's actually part of your visible contract if it's a public type. But then we just call the once we've got the implementation of the foo interface, we can call the methods that are defined on it, and everything's hunky dory. Pointers versus values. Java only has one type of object passing, which is pass by reference. But Go provides two. There's pass by value and pass by pointer. Unlike C++ pointers, Go pointers are type safe and memory safe. So most of the headaches that you would have with pointers from C++ are banished. But objects passed by pointer are mutable, which is what you would expect from the Java world. Objects passed by value are effectively read-only because you're making a copy of them, a shallow copy, I should note. Each time you call a function that takes a pass by value. And Go allows you to control whether the this reference, or not that this is not actually a keyword in Go, but you can call it whatever you want. But I'm using this as a signifier for the concept. So Go allows you to control whether your this argument is passed by value or passed by pointer on a method by method basis. Methods that take this as a pointer can't be called on temporary values, such as a return value from a function that you didn't store in a local variable. And that's because Go assumes that if a function takes a pointer for this, then the function is meant to mutate state. And if it's meant to mutate state, then it doesn't make sense for you to throw away the object immediately after calling it state mutator. So here is an example of two methods implemented on a type. That one of them is passed by value and one of them is passed by reference or passed by pointer. So the basic idea of this type is that it's an accumulator of integers, and then you can ask for the sum later. So you would call record with an integer repeatedly, and record will append the new integer to a list that's internal to the type, and that requires that we can actually mutate the type so that we can update the list. But then when we call sum, we don't actually need to be able to mutate it, so we can make that a pass by value instead of a pass by pointer. And then we can iterate over the list and then add it up into an accumulator and then return the accumulator. So here is an example of that in reality. As you can see at the call time, there is no difference between a this argument that is passed by pointer versus a this argument that's passed by value. For other arguments that aren't the this pointer or the this argument, you would actually have to use the address of operator where you use an ampersand before the type to actually create a pointer to it. Error handling is another area that Go and Java are very different in. Go has a concept, instead of exceptions, Go uses errors. Go technically has a mechanism called panic recover that's similar in functionality to throw catch, but it's deliberately hard to use, and you're not ever really meant to recover from a panic unless you are implementing something like an HTTP server that wants to recover from panics that happen inside of your individual handler threads. Instead, Go has a simple built-in interface called error that functions are supposed to return if they can fail. Go doesn't actually need an optional or a result type, and that's because functions can return 2 or more values at once. Now that Go has generics, you could actually implement such a thing, but Go got away without generics for so long because of the fact that Go can return type tuples rather than just a single type. Go code liners will automatically prevent you from ignoring an error return value. So sticking with the standard is very advantageous because it'll mean that the linter can help you. Here is an example of a function that actually returns an error. I created a relatively simple function that decodes the first Unicode code point found inside a UTF-8 string. So basically, this is a wrapper around a library function called unicode/utf8.decode rune and string. But the decode rune and string interface is a little bit clunky, so we go ahead and wrap it so that we can actually return sensible error values instead of cryptic integers. So what we do is we call the library function, and then we identify some error cases, and then we use format.errorf to construct an anonymous implementation of the error interface that will provide us with a useful error message when it's actually printed. So the error interface is actually just as simple as implementing a function called error that returns a string. So you can implement certain additional methods that can extend the functionality of a basic error, but every error has that as a guarantee. So here we have an example of calling first rune and string, and if the error is not nil, then we print it out using the standard formatter that will nicely format an error by replacing it with the actual error message. Concurrency. Concurrency is very different between Java and Go as well. Java uses these days. Java uses a pure native thread model, but Go is using a hybrid end-to-end threading model. What that means is that since OS threads are relatively expensive, you don't want to create more than a few thousand of them at tops. But Go instead uses a concept called Go routines, which are a special type of thread that's implemented inside of the actual Go application, rather than being implemented directly on top of an OS thread. So these Go routines are extremely cheap because the OS doesn't need to keep track of them. Go multiplexes these Go routines onto the OS threads using a runtime scheduler that gets compiled into your application. And the application, the runtime scheduler in it, is aware of all blocking operations and concurrency primitives. So it knows when a Go routine is about to block, and it can actually reserve that OS thread for the blocking operation if the operation can only block, or it can actually automatically use OS primitives like the poll system call, and then switch between Go routines while keeping the number of OS threads constant. So it's normal for a Go program to actually have hundreds of thousands of live Go routines, even though the Go program only has a few tens of OS threads. Normally, the number of OS threads that Go will allocate is proportional to the number of cores that are available on your runtime environment. When one Go routine blocks, the OS thread switches to another one, and when one Go routine unblocks another Go routine, the OS thread of the first Go routine will automatically switch to the second Go routine. So that effectively means that that one thread can wake up another instantly and take over the time slice of the OS thread without involving the OS level thread scheduler. That means that the OS thread scheduler doesn't actually have to keep track of which Go routines are running. It doesn't even have to be aware that there was any kind of a context change at all, because the Go routines are completely invisible to the OS. Go versus Java. Go routines are not joinable compared to a Java thread, but the Go standard library does include a type called sync.waitGroup that makes it really easy to fake the fact that if you want to keep track of whether a thread is still alive, you create a wait group, you add one for each thread that you're spawning, and then you call waitGroup.wait to block until the wait group goes down to 0. Except for the Go routine that calls your main function. Go routines don't keep your process alive, which in Java terms, that means they are called daemon threads. Java threads have a fixed stack size, which defaults to 512 kilobytes. That means that each thread is taking up half a megabyte of stack, whether you're using it or not. Go routines start with a 2 kilobyte stack size, but it can only get away with that because each Go routine can actually grow its stack dynamically as needed. So if an individual Go routine and it needs a deeper stack than that, it will allocate more, but it doesn't have to plan ahead for the largest possible stack, which is what Java has to do. One other nice thing that Go has is channels. It's a built-in concurrent data structure. Channel allows you to build very complex algorithms that share data only by a message passing instead of via shared memory. That means that you can write a lot of your code without ever having to keep track of mutexes or other synchronization primitives. You can just use channels. A channel can be buffered or unbuffered. A buffered channel works like a fixed capacity concurrent queue. You put some work in on one end and you pull some work out on the other end, and the queue can hold up to some number n of work items, and putting work into the queue will block if the queue is already full. An unbuffered channel works kind of like a mutex or a condition variable. You try to write to the unbuffered channel, and you block until something is ready to read from the unbuffered channel. And likewise, if you read from an unbuffered channel and there's nothing in there, then of course you block until somebody writes. So that means that it's a pure handoff, where it's like it's essentially like one thread passing a mutex, an open mutex to another thread, or a condition variable where you write to a shared location, and then you signal to the condition variable that the consumer of that variable should wake up. You can read from or write to multiple channels concurrently in a single operation using the select statement. The select statement guarantees that only one select case will ever run each time you run the select statement. So select is normally used in the body of a loop. Essentially, it will pick one of it'll pick the first select case that's capable of running. If multiple select cases become capable of running at the same time, it'll pick one arbitrarily. So here's the longest part of my presentation, which is a complete, actual worked example of using channels and multi-threads to implement some actual functionality. This is a type called Mongo Batch Writer. And the idea of Mongo Batch Writer is that we are trying to batch up writes to MongoDB so that we can reduce the amount of traffic between the client and the server using bulk operations. Basically, we are keeping track of the Mongo client itself. We're using a wait group to keep track of all the outstanding threads for when we're trying to shut down cleanly. We keep a channel that will be used internally for incoming writes, and that's called write-chan. We keep a thread that does flushes, and that thread is asynchronous. So when somebody asks for a flush, we need to be able to do the flush and then tell them that it completed. And we do that by using nested channels. I'll give some example, an example of how that's actually used in a little bit. And then there's a done channel used internally that lets us know when an individual bulk operation completes, so that we know that we can tell when the flush completes. Because the flush will require that all all bulk operations of a ID number less than or equal to when we started have completed. Okay, so the new Mongo batch writer is a function that we're using as a constructor wrapper. Basically, all it does is populate the fields, make sure that the channels are actually allocated, and then we create a thread called the gatherer thread that will do the actual channel polling, and will build up batches and then send them out to flush threads as we need them. And since we're spawning a thread, we add one to the wait group, and then later we will block on that wait group to verify that the gatherer thread has closed. Here are the implementations of the public methods: write, flush, and close. For a write, we just send it into the write channel. For a flush, we create an unbuffered channel that takes no data, and then we send it into the flush channel, and then we block until our wait channel is closed, and that will let us know that the flush that we requested has been completed. So writing to the flush chan is a request that we want to start a flush, and the wait channel being closed is our confirmation that the flush is completed. So the wait chan read is expected to block until the flush is complete. And then we close the Mongo batch writer by closing the write channel and the flush channel, and then blocking until the gatherer thread has completed, plus all flush threads. This is a rough outline of the gatherer thread internal code. We build up a queue, which is a pre-allocated array that has capacity for up to 1,000 items. That will automatically grow later. We're just guessing the maximum number it should ever have. But although in this case we actually never exceed that. We create a ticker that flushes automatically every 30 seconds, even if nobody has asked for a flush, and that guarantees that if we have fewer than 1,000 writes, they will eventually make it to disk in at some finite amount of time. And then we loop on our select statement. As you can see, the select statement syntax is very similar to a switch statement. We read from our write channel, flush channel, and done channels. For write and flush, those can be closed. So we take the 2-argument form of a channel read, where the second argument is a Boolean, letting you know if the channel was successfully read from or if it was closed. OK will be true if we actually got data out of the channel. OK will be false if the read completed because the channel was closed. I have omitted several passages of error checking and checking of the OK values. So this is very simplified from the real code, but it should give you the flavor. Basically, if we receive a write, we add it to the queue. And we call an internal function, which is actually defined as a closure, called flush, that will only do a flush if 1,000 items are in the queue. And then if we read from the flush channel, then we start a flush that will flush even if there's only one item in the queue. And then we add the resulting wait channel to notify the caller to the list of blocked flushes, where a blocked flush means that there is a flush thread currently active, and we're waiting for the done channel to report that that flush ID has actually been completed. And then when we when we receive a read from the done channel is written by the individual flush threads. And then we call a closure called done that does the actual logic of calling all of the wait channels. And then whenever our ticker ticks every 30 seconds, we also do an unconditional flush, which is a flush that has a threshold of one or more items. And then when we're done looping, because the OK returned false, then we stop the ticker, we do some cleanup work, and then we call waitGroup.done to let the close operation know that this thread has completed. Blocked flush is a very simple struct. We have a couple of state variables that were omitted from the last listing that are internal to the gatherer thread. And flush is defined as a closure inside the gatherer thread that just does a few things that use those state variables. Basically, all we're doing is we're allocating a new flush identifier that uniquely identifies this flush operation. We're adding it to the list of flushes that are currently pending. And then we create a flush thread and add it to the wait group. And then when a flush thread completes, we delete it from the list of active flushes. We increment the done counter to know to the maximum that we can, so that done flush ID should equal the highest flush ID that has been completed so far. And then when we go through the list of blocked flushes, if the done flush ID is greater than the flush ID that the blocked flush is waiting on, then we go ahead and close the notification channel. Otherwise, we keep a copy of it for the next round, for the next time done gets called. The flush thread is actually fairly simple. All it does is grab a handle to the Mongo collection and then call bulk write. And it does some error checking, and we use defer to guarantee that some code runs, most notably writing to the done channel and telling the wait group that this thread has completed. As explained in the comment, defer is sort of like a Java try finally block. Okay, that's the entire worked example of Mongo Batch Writer. So some of these features that Go has, the Java folks have actually been inspired by, and they have a Java enhancement proposal. I believe that's what that stands for, to implement a feature called virtual threads. Virtual threads would basically be be Go routines for the JVM, where you use a hybrid threading model. And I believe they're also trying to reduce the stack size so that the stack size is growable. There is no word yet on whether channels or select will come to the OpenJDK, but that will probably be a future JEP implemented separately from the actual virtual threads JEP. For more information, search for Project Loom. It's coming as a preview to JDK 19, I believe. We'll see if it actually makes it to production for the next stable JDK. And my final section: memory use and usage and optimization. Go and Java are very different in this respect. The biggest thing is that it's easier to be memory efficient in Go. Go is a lot more aggressive at placing local variables on the stack. All allocations are subject to what's called escape analysis, And escape analysis determines whether or not any pointers to an object outlive the scope where the object was allocated. So if none of the pointers outlive the scope where the object is allocated, then the object can actually be allocated inside the stack of that scope. And that means that at compile time, if you can prove that the memory will never be referenced after the function call ends, you can make it just part of the function call stack. And stack RAM is extremely cheap to free because freeing stack RAM is just changing a pointer. It's essentially a stack. A stack is essentially a bump allocator for an individual thread. And bump allocators are the cheapest possible allocators. The problem is that they don't let you free things in arbitrary order. Go's escape analysis is very powerful because Go actually does full program optimization at link time. And that means that Go can actually see not just what functions exist in your current package, it can actually see what functions exist in the entire program. And it can actually see that the functions that you're calling do or don't hold on to pointers to their arguments. Go makes it easy to embed the actual bytes of one complex type inside of the bytes of another complex type. Java requires that each Java lang object has to be allocated individually and usually on the heap. So only primitives, Boolean, int, long, short, et cetera, can actually be embedded directly into your object. Anything that's a class has to be allocated as a separate object. And objects have overhead. Go has 0 overhead at runtime for embedded types, but Java implements a bunch of fields that are related to garbage collection, and each Java object also implements a mutex so that the synchronized keyword can work. That adds up very fast. The overhead for a single Java object on 64-bit, I don't remember exactly what it is, but it's on the order of 32 to 64 bytes per object. So comparable server programs written in idiomatic Java versus idiomatic Go are often 10 times more bloated in RAM use, in my experience. For example, a server that takes 512 megabytes of RAM at runtime in Java can often run in 50 megabytes of RAM at runtime in Go for the same load and the same use case. Basically, the garbage collector is vastly different because Go takes advantage of 25 years of language design history to have one of the best garbage collection systems in wide use, beating Java in most ways. That's a very bold statement because Java's garbage collector is known to be one of the most advanced garbage collectors in the industry. Here are some of the differences between the Go garbage collector versus OpenJDK's garbage collector. Or default garbage collector algorithms. Go never defragments or consolidates heap memory, and that's because Go is designed for 64-bit architectures, and there's no longer any real need to do this on a 64-bit architecture. Basically, defragmentation is important if you have a limited amount of virtual address space, but if you have 64 bits of address space, you're never going to use it all. So there's no worry about fragmentation. And because there's no defragmenter, Go never moves objects around in RAM. And because Go never moves objects around in RAM, stop the world pauses are extremely short and extremely rare. Go is conceptually similar to JVM's incremental concurrent mark and sweep, but incremental mark and sweep mode can hit what's called a concurrent mode failure when threads are allocating memory too quickly. But in Go, Go routines that outpace the dedicated garbage collector threads, if they're allocating memory too fast, they get those Go routines get temporarily descheduled, and the OS thread gets forced into doing garbage collection work, and that helps the garbage collector to catch up. And that does add some latency to your program if you have heavily allocating threads. But it does mean that it's the threads that do the allocating that get punished. It's not the threads that are running that are being nice to the garbage collector. So if you have some threads that are messy and other threads that are very clean in terms of how much allocation they do, then it's only going to be the messy threads that get punished. And therefore, any thread that you write that is nice to the garbage allocator, nice to the garbage collector, will also give you nice latency. Java's garbage collector algorithms are tunable, but they are too tunable. They're notoriously fiddly. You have to tune them correctly, or they will give you terrible performance. You have to tune them correctly, or they will stop your application for ridiculously long periods of time. In contrast, Go's garbage collector has almost no tunables. Go does not use generational heap. That's what the stack is for. The variable environment variable Go GC specifies the ratio between objects found live during the last garbage collector pass versus the objects allocated since then. So Go will dynamically resize the maximum heap size up or down to pace with object allocation rates. So if objects are being allocated too fast, then the max heap will be grown, and that will slow down the number of garbage collections needed. And if object allocation rates then slow down later, it will actually decrease the heap size so that garbage collections happen more frequently. And it will try to maintain a specific ratio of objects live versus objects allocated in order to tell the garbage collector thread how often it should be running. There's one noteworthy downside to the Go garbage collector, and that's that Go doesn't provide an easy way to tell the garbage collector that you would rather waste RAM than waste CPU. But there's a solution to that, and it's called a ballast. A ballast is a chunk of garbage that you deliberately leak, and then you never access it again. And ballast doesn't count against your RAM usage as far as the OS is concerned, because you never actually read to or write from it. So it's created zero allocated, and then but those zero pages are actually lazy. And if you never actually read from them or write to them, they never get physically allocated to physical RAM. So it only tricks the garbage collector in Go into believing that you have 1 GB more of heap usage than you actually do. Questions?
Okay, we have 5 minutes for questions. Do we have any questions?
Going once, going twice. Sold to the beautiful nobody.
Thank you very much. It was a really great presentation. I'm going to stop my recording now, so